Okay, please come back and take your seat because it's time for Marco Napetti to talk us about from Ruby to Rust, the RustLab porting experience.
Welcome everybody to my first talk. So let's start. Hello everybody, my name is Marco. I'm a software engineer with more than 15 years of experience. Not 50, I'm not that old. And I actually work for TheRockTrading, the oldest crypto trading platform in Europe, as a software engineer. I started studying Rust in 2017. After a talk by Michele D'Amico, I fell in love with the language. I started studying it. I never wrote a single line of Ruby, so it will be an interesting talk about Ruby. And this is my first public speech ever, so please be kind. So the porting started in mid-2021. It isn't ended yet. The project is still alive. The code base, the Ruby code base is still alive. So we must sync with the new commits, and it's hard work. We are splitting the Ruby monolith into several Rust microservices, without losing compatibility, improving performance and reliability. So it's a big job. So Ruby defines itself as a dynamic open source programming language with a focus on simplicity and productivity. It has an elegant syntax that is natural to read and easy to write. Rust defines itself as a language empowering everyone to build reliable and efficient software. The goals of the two languages are quite different. Ruby aims to be simple and easy, while Rust aims to be reliable and efficient. Ruby is still a live project. It's releasing version 3.2 soon, but its popularity is decreasing year over year. While Rust is fast evolving, it has a new stable release every 4 weeks, and the last one is the 1.64. There are not projects for a Rust 2.0 because Rust uses additions to seal functionalities inside and permits a better backward compatibility. That means that anything that wrote against a particular edition will still build even using really new compilers. Actual Rust editions are 2015, 2018, and 2021. Ruby is interpreted. That means that you need a Ruby runtime installed to execute a Ruby program. While Rust is compiled, that means it outputs an executable that only depends on libc to work. And it's not always true. Maybe you wrote something bare metal. Ruby is historically dynamically typed, even if with Ruby 3 they introduced a non-mandatory typing, while Rust is strongly typed with a smart compiler that often can guess the right type for your variable. Ruby is garbage collected. That means that at runtime there is a dedicated parallel process that frees memory occupied by unused variables. Where Rust is borrow checked. That means that the lifetime of every variable is defined at compile time, and you can't occur on, for example, use after 3 errors. Ruby uses inheritance, while Rust uses composition. Inheritance is when you design types around what they are, while composition is when you design your types around what they do. Okay. So there are already been lots of talks, blogs, and how-tos about how to build a web server in Rust. For example, Sunday, Marco Ieni kept a really good workshop about it. In this talk, we'll cover only a Ruby on Rails ORM that's called active record. More, we'll get a sample of Rust no magic. In Rust, there is nothing magical. Everything happens for a clear reason, and that reason is always a trait. For example, you can use the for operator on everything that implements the into iterator trait. Even macros are magic. They simply output Rust code that you could write yourself. You can use a tool like cargo expand to look at the generated code. I'll divide this talk in 3 parts. The first part is the story of how I've chosen the right ORM for the project. So, in 2021, there were only 2 major ORM for Rust. There were Diesel, a really old code base, almost unmaintained. There were no new releases since years or any minor fixes. Not first-class async support. There was a third-party plugin, but it was kind of a knack. And it wasn't full Rust. It used the C bindings to use the native drivers for the various databases. And there was CRM. It was a brand new project based on SQLX. And was a sync first, full Rust, but had many missing features, because it was a brand new project. It seems like an hardcore choice, but in fact, the async first and being for Rust for me was key features. Also, being an active developer project helped a lot. It's also true that they resumed the Diesel project and released Diesel 2.0 a few months ago, but it was 2021 for me, so I can't predict the future. As I just said, CRM was missing a lot of key features, so I rolled out my sleeves and started working on it, contributing to the project. As you can see, I'm the 4th contributor ever, behind the 2 owners of the project and another guy who contributed before me. My first contribution has been a proc-macro, a procedural macro, to auto-generate the boilerplate code. For example, if you had a 10 fields model, before my proc-macro, you had to write around 40 lines of codes. Only for the boilerplate is a big chunk of code. While using my proc-macro, you write 15 lines of codes. Is a big reduction. More, I've implemented transactions, logs, query result streaming, and the metrics observability. On the second step of this talk, we'll get a bit technical. We'll see some Ruby code and a lot of Rust code, so fast your seatbelts. This is the active model we'll use as a reference. I hope the code is readable. Hope so. Since I told you in the beginning, I never wrote a single line of Ruby in my life. So we'll need a bit of investigative capacity to write this code. So we'll ask for the help of Lieutenant Colombo, a famous player, famous character played by Peter Falk. First of all, we define the model extending the active record base class, pointing to the database table, my table, is an example. More, we have a scoped filter named active that adds a where clause to the current query on field status and active value. We have a metadata field that contains JSON data. We have a cached method that on first call inits local static variable cache with a return value from the chaining of the scoped filter active and the static method do something expensive. In the end, we have the do something expensive method that iterates on actual query results, filtering only elements with the metadata parent ID equal to the input ID. Quite simple. Here we have I hope the code is readable. The Rust code, don't worry about the code block because it's only the CRM boilerplate. What I told you with my proc-macro is shorter, really shorter. In Ruby, fields are not named if not required. So here we need to describe the full table because Rust is strongly typed. And even the JSON fields needs a type to be described. So we use only what we saw in the Ruby code. CRM has several concepts that repeats for every table. There is the model that it's a read-only data representation. You can use it in query result sets. Active model is a write-only data representation. You can use that in inserts and updates. Relation is a schematic representation of foreign keys. Here we have none. And the entity is the entry point to execute queries on the table. We'll put everything in our ORM module, submodule. We'll see later why. We use a trait to simply add a method to CRM selection struct. This way we reach the same functionality as a Ruby scoped filter. Our scope trait only requires CRM query filter trait to be able to use the filter method on this default implementation. This way we are able to implement the trait for select over our entity without worrying about specific code. We wrap every CRM model inside our struct and use a Tokyo one cell to create a variable that can be initialized only once without need of internal mutability. At this point, maybe you guess the pattern. We use from trait to create a constructor for our wrapper and the ref to trait to obtain a limited type of inheritance. It's not really inheritance, don't get fooled. Using this trait, the wrapper can behave like the inner field, gaining its methods, but only when there is no mutability involved. This is possible because the compiler automatically dereferences when needed. This is widely used in the standard library. For example, vec, the ref to slice, and the string, the ref to string slice, sorry. Here we have some advanced concepts. Please don't panic. Our do something expensive method asks for an integer ID and an optional, or if you prefer, nullable base query. The return type is a result, so a fallible operation that, when successful, contains an opaque type that implements the stream trait. So an async iterator. And iterates over results that, when successful, contains our model. The error type for both results is the IB error, is the CRM error type. Why do you use opaque types? Well, this is really helpful because in places where there are types that are really hard to name or even unnameable. An example of really hard to name types could be a composite type, like streams. Every time you add a stream operator, you're adding another wrapping layer on the stream type. After a few iterations, you end up with a really huge long type that you really don't care about. You only care about the stream trait. So you simply need to have the trait. An example of a nameable type is when a closure is involved. Closures have nameable types, so you're often forced to use template or dynamic dispatch. Our code falls in both those cases. Inside the method, we simply use a plain select star if a base query wasn't given, retrieve a connection, and execute the query asking for a stream of query results. If the query is successful, we filter the models by parent ID. and convert it to our wrapper model, because the query is still returning the base model, the base CRM model. Some of you may have noticed this is a workaround. This method could have been a trait attached to the selection struct, like our scoped filter. Maybe it's worth to open a parenthesis on this topic. This is the ideal version we want. We have a model stream type to reduce type complexity, and it's exactly what we were doing before, an opaque stream of results containing our model. We have our sync scope trait, but it's time we can't be general over another trait due to CRM design. So we need to write an implementation specifically for the selection trait, selection struct. Sorry. The code is quite the same as previous slide, except for we are working inside the selector, hence we don't need the optional query in input. Nobody ever told that Rust is a perfect language, and neither it's a complete language. As I already told, Rust is fast evolving. There are lots of improvements being discussed and introduced at every release. The workforce isn't infinite, and sometimes a new feature depends on another feature to work. Therefore, some parts takes longer than others to land on stable. This is the case of our RFC 2071. Without it, we can't return input trait from trait methods, and we can't have async methods in traits. That is the same concept. An async trait is nothing more than a method that returns input future. Remember, there is no magic in Rust. Just to let you know, there is a workaround. It implies using dynamic dispatch and heap allocation, and therefore it's less performant than the previous version, more or less at 10% less performant. As you can see, the code is really similar, but instead of input trait to obtain an opaque type, we use pinbox dyne trait. That means pin ensure the compiler the value can't be moved from its place in memory. This is really important in async code, because otherwise things can be moved while the task is in standby. And on wake up, we end up in an invalid state. The box indicates an heap allocation. That means the memory area is not directly dependent on our method. And dyne indicates dynamic dispatch. At this point, the real identity of the type is lost. Only the trait remains. Most of this work can be done using the async trait crate that does exactly the same using a macro. As always, there is no magic in Rust. Coming back to our implementation, we have the cached method, that last piece of our mosaic. The code here is quite simple. On first call, we'll init the value of our cached variables, collecting inside it the contents of the stream of query results coming from the do something expensive method. From second call, we already have the value stored, and we return that. Time for benchmarking. Mean time for cache method on Ruby is around 1 millisecond. Mean time for cached method call on our Rust implementation is around 130 milliseconds. We are like 8 times faster. And probably there is room for a lot of optimization inside CRM, because it's still a young project. You can find all the code, both Ruby and Rust, and the benchmarks on my repo, linked there. If you are thinking we have reached our destination, you are wrong. We can go further. For example, storing dictionaries in memory and reaching near zero access time. Let's see how. Let's take, for example, a table of measurement units. Data like that probably never changes, but it's still useful to have that in a database table for foreign key checks and maybe sharing between services, other services, maybe written in different languages. Storing this kind of data in memory, for example, at application startup or updating at regular intervals, will reduce data access time to near zero. Let's see how we can do that. Using a read-write lock is the easiest way to obtain a shared dictionary. On access, you read lock it, and that means that the read is almost lock-free if there aren't concurrent writes. What are the cons of that implementation? Well, there is a lock involved. That means if there is a concurrent write, we end up waiting for it to end. And we lose our near zero access time. More, the method to access the dictionary is async. It's not a real problem, but it could be an ergonomic problem since, for example, inside most places that accept closures, it's not possible to use async. For example, option map, result, and then, and stuff like that. What if we are able to update the same without using async? Using arcswap, we we can literally swap our dictionary data without anybody noticing. The operation is literally atomic. If someone was reading the data during the swap, will still point to the old version, and as soon as nobody is reading, the old version will be automatically dropped, so free from memory. Now the access operation is sync. We solved our sync problem. What are the cons of that implementation? None, apparently. But we still have to check that the key we used is really exists inside our dictionary. Remember our measurement unit table. How can it be that millimeters vanished for our dictionary? If it happens, it would mean that there is a big problem, a bigger problem. For example, our database is offline, or maybe someone has dropped our table. Or maybe our company dropped the support for millimeters because our company stopped working with it. Well, maybe we stopped selling at 99% of all countries. That will mean that all the code explicitly referencing millimeters must be corrected. What do we do? A full search inside the code is not the best. What if we can do better than this? What if the compiler can do this work for us? Using a procedural macro, we can solidify table data inside an enum. Primary keys will be the enum variants, and accessory fields like our family, description, or decimals will be instance methods. Constructors at this point simply needs to match the primary key existence. Obviously, you need a rebuild of the application if the data changes. But is it just a dream? Let's see. Using my symbols macro, you can do exactly all of this. All you need to do is to write your CRM modules and a function to retrieve database connection. It even creates cache files in your type folder, so you can even work offline after first run or light up build times. As you can see, measure units enum is empty because it will be filled by the procedural macro. In the example, the type for the field family is changed from the original string to our enum family. Now calling the family method on a variant of measure units would return a family enum variant instead of string. trying to use a non-existent variant would result in a compile error. We have retained data integrity check at compile time. In conclusion, we can reach feature parity and even go further without writing much code, with a big performance boost, but more importantly, using idiomatic code. So we reached the end of my talk. I'd like to thank a lot of people, you all for being here, RustLab organizer for their hard work, my company, TheRockTrading, for this opportunity, and the RustLang IT Telegram group friends for personal support.
So, thank you very much. Is there any question for Marco? On there?
Please be kind.
That's an interesting journey that you've been on. One question I have about, I have been through Rails and a lot of, what was the right word, monoliths. And one of the advantages about monoliths is that you do all of your authentication and your authorization in certain places, and then, things just happen, right? So one of the challenges that I've seen with people doing microservices is that they have to figure out how they're passing whatever authorizations they need to do and permissions into the microservices. And I'm wondering whether there was any facilities in Rust that made your life easier there, or did it matter? And how did you hook that up to the microservices did you hook them up behind the monolith to accelerate things, or did you have front ends that reached out directly to the microservices?
If I understand correctly your question, we have done everything on the API. The model is slightly a porting of the table, and it's agnostic. It doesn't know everything. And we share the models between the microservices. It's not the microservices way, but we prefer to not duplicate code.
Mean that your front end, your end applications, web browsers are reaching directly into your microservices?
No, those are internal REST
internal
APIs.
RESTs from the monolith on your front end onward. So you didn't worry about authorization because it's implied.
There is authorization, but it's internal. It's based on the user ID, for example, that is accessing the API.
Thank you. Any other question? Seems not. So thank you very much. Given we have some, thank you very much for Marco.